What I want to talk about is a series of works that have to do with many papers I wrote throughout the past decade, and also works that Paul have been pursuing from Colorado. But in particular, I want to focus my talk on 3 papers done in collaborations with Alex Serantes, Michal Spaliński, and Ben Withers, as well as an earlier work that involved also my past PhD student, Victor Svensson. And all these works, have in common relativistic hydrodynamics and, as it turns out, a notion of causality. So let me start with a broad context. And as I said, like some of motivating questions go back in time to all the way to 2011. So relativistic hydrodynamics, understood in modern way, is an effective field theory of transport of energy and momentum in relativistic systems, such as nuclear matter at RIC and LHC, or quantum field theories, in particular holographic quantum field theories that are described in terms of dual gravitational spacetimes. And of course, in relativistic systems, the energy and momentum is encapsulated in terms of the energy-momentum tensor. And the general energy-momentum tensor has 10 different components that are subject to 4 conservation equations. And in my talk, basically all the things that I have to say generalize to arbitrary number of dimensions, but for definiteness, I will stick to 4 macroscopic spacetime dimensions. And relativistic hydrodynamics is built on the premise that if you wait long enough, the number of degrees of freedom understood as independent components of the energy-momentum tensor reduces to these specifying a local equilibrium state. So a local equilibrium state is going to be specified certainly by temperature, but if we want to be more general, maybe we're going to say energy density. Perhaps there are other obvious conserved charges, such as charge density. But also there's going to be a hidden parameter here, which is a boost parameter with respect to the local rest frame. And in the end, we're going to come up with this way of parameterizing the local equilibrium state. So there's going to be, say, effective temperature as 1 degree of freedom and 3 degrees of freedom sitting in a 4 velocity vector that is unit normalized that tell you how far away you are from a local rest frame. And now if you promote, say, local temperature, and actually they've already been promoted, and velocity to functions of space-time coordinates, then conservation of this energy-momentum tensor give you a set of differential equations that in principle is well posed, and give you a physical theory called perfect fluid hydrodynamics, the name perfect coming from the fact that there is a conserved current, exactly conserved current, and this conserved current corresponds to the lack of entropy production, absence of entropy production. However, realistic fluids, realistic systems dissipate, and in hydrodynamics, this is encapsulated by the corrections to the perfect fluid descriptions, right? So like if we're just interested in perfect fluid, we would stick to this, and often it is the case that one sticks to this and one is not interested in anything more. But in particular, in the context of nuclear collisions, it's important to include these correcting terms. And as I said, relativistic hydrodynamics should be understood as an effective field theory. So there's going to be an underlying derivative expansion in which these corrections to the perfect fluid description are given in terms of derivatives of hydrodynamic variables, so derivatives of velocity and possibly of temperature as well. And to the leading ordering derivatives, the dissipative term is given by the shearing correction to the energy-momentum tensor, so a derivative of velocity that is transverse to the velocity. There could be also a term that has to do with the expansion or contraction to the fluid. And then these tensorial structures are multiplied by scalar coefficients These scalar coefficients are called transport coefficients, and here in this equation, this is the shear viscosity and the bulk viscosity. And then this is an effective field theory, so you keep going and you add terms of higher order in derivatives, in particular at second order. If you talk about conformal fluids, so fluids for which in particular the trace of the angular tensor is 0 in flat space, at second order there are 5 terms, at third order there are 20 terms. And in this case, also the bulk viscous term vanishes. So the bulk viscosity by definition is 0 because the trace of the angular tensor is 0. So understanding corrections to the perfect fluid description, so understanding like this, what kind of structure is here, what kind of terms are there, is interesting for several reasons. Like, first of all, including these terms allows for dissipation. Secondly, if you think formally about equations of motion for hydrodynamics as coming from the conservation of the energy momentum tensor, then inclusion of these terms also influences the properties of solutions of hydrodynamics because it alters the form of the equations of motion. And particularly of this reason, it is of interest to phenomenology at RIC and LHC. So in the course of the past 20 years or so, there's been a lot of progress in understanding relativistic hydrodynamics in various ways to improve our understanding of what's possible, what's not possible when it comes to nuclear collisions and many other topics. So arguably, when it comes to relativistic hydrodynamics in the first decade of the century, the mindset was primarily twofold, and please disagree with me if you think it's not appropriate to say it. One aspect of this mindset was to compute first and second order transport coefficients. So to compute what's the value of the shear viscosity, what's the value of the bulk viscosity, what's the value of some of these terms sitting here for various microscopics. So for holography, for various holographic models within holography, for kinetic theory, and possibly for some phenomenological models. So that's one aspect of the mindset. And then another aspect of the 2000s mindset, and I'm gonna come back to these aspects. That's why I'm listing them. Is this Coughton-Son-Starnet's conjecture that was based on the observation that the ratio of shear viscosity to entropy density, so a very nice dimensionless number, as calculated in holography, say for n equal to 4 super-Yang-Mills gauge theory at large number of colors and strong infinite Hooft coupling, is 1/4 pi in natural units. And now if you look at other fluids, not necessarily relativistic fluids in nature, this ratio for holography is about an order of magnitude smaller than the ratio for the other known fluids. So what they did in 2004, and what was very influential for the development of the field, was to propose that there is a bound on transport, to put it plainly, and the bound is such that shear viscosity over entropy density is never smaller than 1/4 pi. This was a very influential idea. We know now that 1/4 pi is not a lower bound for shear viscosity that you can get using controllable quantum field theory models below 1/4 pi, albeit infinitesimally below 1/4 pi. So the current status of this is that there might be a lower bound, but we don't know exactly what it is. But the take home from this is that putting bounds on transport is an interesting idea, and I will come back to this later in my talk. So, so that was 2000s. Now, coming back to 2010s, an important topic in the past decade of the 21st century was studying the emergence of a relativistic fluid. So these works were done literally in the context of theoretical modeling of ultrarelativistic heavy ion collisions at RIC and LHC. So what you see here is an artist picture, actually Alexis Mazalyaska's picture of a nuclear collision in which we have two incoming nuclei. We suppress the directions. I mean, these nuclei are highly Lorentz contracted, and I suppress here the directions in the perpendicular plane. So I just plot the longitudinal direction and time. And as a result of the collision, at least at late enough time, and at least like in the central rapidity region, we would expect fluidity to appear. And of course, given this expectation, it was very interesting and important to observe it explicitly in microscopic models of nuclear collision. So in this context, in QCD. In QCD, of course, it's very hard to do this calculation. And in fact, I believe the first calculation in something that was microscopic was done in the context of holography by Kessler and Jaffe. And in 2011, with my collaborators, we came with one realization of such calculations. Let me discuss this plot. So this plot shows effectively the expectation value of the energy-momentum tensor of holographic quark-gluon plasma. In fact, like it shows a ratio of various components. The details don't matter really much. What you see here on the x-axis is some particular clock variable time, and the three different curves correspond to three different non-equilibrium states that you initialize basically here at the moment of the collision. And what you see here is that if you wait for long enough, and in fact you don't have to wait for very long, these three different non-equilibrium states, as from the point of view of the expectation value of the energy-momentum tensor, are very hard to distinguish. I mean, basically all three curves collapse on top of each other. And this collapse on top of each other is preceded by, as it turns out, exponentially decaying and oscillatory behavior. So in particular, if you are a bachelor student and you want to do a data analysis on this data set, what you would find out is that there's an extremely good fit to the tail here that is going to be a simple parallel, possibly with corrections. And then what comes on top is something that is exponentially decaying and oscillatory. So over here, this hash has both real and imaginary part in holography. So what I was showing for you was the Bjorken flow. So the dynamics following from a model of a nuclear collision in which one assumes that the system is boost invariant with respect to boosts along the collision axis. And in boost invariant flow, like the derivative expansion of the dissipative part of the energy-momentum tensor, so non-perfect fluid part of the energy-momentum tensor, can be mapped into a late time expansion of this quantity A that was depicted on the y-axis, and eta over S. So the shear viscosity to the entropy density ratio is encoded in A1 in the first coefficient. So the one that was directly visible here. So the height of this is set by eta over S, and of course this is the same theory, so the value of eta over S is the same, so all these curves are on top of each other. And then A2 corresponds to terms with two derivatives of fluid variables, etc., etc. And it turns out that if you look at this closely, what you're going to find out is that the AN corresponding to the term with nth order of derivatives, with this number being large, these coefficients behave actually like n factorial. So what it means is that at least in this setup, and now we know that it is much more generic, the derivative expansion of relativistic hydrodynamics is an asymptotic series with a zero radius of convergence. And that's a topic on its own, but I don't want to dwell into it very much. What I want to signal is that if you have such a divergent series, a standard tool is to bring a series that has a zero radius of convergence into a series that has a finite radius of convergence by basically dividing out this factorial behavior. And then once we have a series that has a finite radius of convergence, we can extend it past the radius of convergence onto a larger portion of a complex plane by using Padde approximation, which is to truncate this series and represent the truncated series at a finite order as a ratio of two polynomials. So for example, here we can calculate about 200 orders of the expansion and represent this polynomial of the order of 200 as a ratio of two polynomials, each of the order 100. And now, if you look at the singularity structure of this approximate analytic continuation, what you're going to find out is that the singularity structure knows about the values of these exponentially decaying and oscillatory contributions to the engine-momentum tensor. So basically, what it shows is that relativistic hydrodynamics doesn't exist on its own. It knows about stuff that is formally not capsulated by it, at least not by any finite truncation of the derivative expansion. And these transient effects that I'm depicting here are closely related to shortly lived quasi-normal modes of black holes in anti-de Sitter space. So, yes, of course.
Are we conformal or not?
So in this setup, we are conformal.
Okay.
And later in the talk, I will drop this assumption. But for this slide, we are conformal.
And do you think your statement that it knows about non-hydrodynamic stuff is related to the fact that it's conformal, or is that a general statement?
No, I believe it's really way more general. And I will show you indications why I believe it's way more general.
Okay, thank you.
Of course. Anything else? Any other questions? Yeah. So the punchline of this is that there's this is basically a smoking gun evidence that relativistic hydrodynamics is not there, at least upon including dissipative effects, is not there on its own. It knows about the existence in the system of other excitations that are short-lived, with relativistic hydrodynamics being a description that allows to frame excitations that are arbitrarily long-lived. So this was a particular solution of nonlinear non-equilibrium dynamics. Non-linear non-equilibrium dynamics is difficult. So what's easier is to look at the linear response theory. So let me rephrase some of the things that I told you in the language of linear response theory. Let's imagine that we have a global equilibrium state given by a density matrix, thermal density matrix, and what we have is we look at a perturbation of the system that is triggered by a source that couples to some local operator. And now the response of this operator, like the change of the expectation value in this operator, is given by a convolution of the retarded two-point function in a thermal state times the source. And this two-point function is evaluated in an equilibrium state. So of course, this is to the leading order in the amplitude of the source, in the amplitude of the distortion of the system. You can go to higher orders and include nonlinear effects in as a perturbation theory on top of equilibrium. That's not going to be the subject of my talk. And now, when you look at this expression, you see that this expression is nicely written in Fourier space. And now, in particular, what I did is, which is customary, is to pick a spatial momentum. So this P is a spatial momentum of the response of the system, but I kept the time dependence intact. And now, in order to obtain the time dependence, what I have to do is I have to evaluate this integral on a by taking this integral in principle originally along the real axis, right? Because the frequency here, the frequency here is integrated over the full real axis. But we don't have to do this. I mean, we can deform the contour, and in particular here, it's advisable to deform the contour to the bottom. And now, when we do this, the contribution from the real axis integral can be replaced by the sum over the contributions from the singularities in the lower half plane of the retarded two-point function. And it turns out that in holography, for operator, there's a conserved current. So in this case, I took it to be a particular component of the Angel-Newton tensor. The singularities are just the single poles. They come in pairs, so that they have oscillatory and decaying part in this case. There's going to be a singularity whose frequency is going to approach zero as spatial momentum goes to zero. And this is this singularity that, as momentum is lowered, it traverses all the way to the origin. And the singularity is nothing else than a dynamic sound wave whose dispersion relation is going to take this form. So alpha 1 is going to correspond to the speed of sound. In conformal field theory, in 1 plus 3 dimensions, the speed of sound is going to be fixed by the trace of the Angel-Newton tensor, which is epsilon equal 3p. So the speed of sound is 1 over square root of 3. Then beta 2 is going to be given by the sound attenuation length. It's going to be sound attenuation length, basically. And it's going to be related to the shear and, in general, bulk viscosity, etc., etc. And then on top of this, what you see also are transient oscillations, such that as spatial momentum goes to zero, they don't go to the origin, they don't become long-lived, they decay exponentially, and after a while, they are gone from the dynamics of the system. So this is the picture of linear response theory of what would happen if you study non-equilibrium physics for small perturbations of equilibrium, in opposition to this being big distortions around equilibrium. Any questions about it? No. So let's keep going. So this is basically how linear response theory have been discussed for many years until the year 2018, when my collaborator Ben Withers came up with a beautiful idea. And this idea was discussed by him in the context of holography, but one does not have to do holography to convey exactly the message. So in order to tell you like what Ben did, let's consider a diffusion equation. So this is a diffusion equation. Diffusion equation arises approximately in the description of relativistic hydrodynamics. In particular, if you look at perturbations in the shear channel to the leading order in derivatives, the non-trivial dynamics in the shear channel reduces to the diffusion equation. And the diffusion equation, it violates causality, which is basically the reason, one of the reasons why relativistic hydrodynamics, as discussed in Landau and Lifshitz, is not causal. And the way to see that it violates causality is to start, for example, with delta function initial condition for psi, and you see that in the diffusion equation, this spreads immediately to a Gaussian, with a tail extending to arbitrarily far away from the origin. So clearly, like over infinitesimally short time, you suddenly have a support, go from zero support to an infinite support in real space, and this is not causal. Somebody had a question? Because I don't see all the faces. No.
I don't think there's any questions yet.
Okay, so it was like a background noise. Good. So this equation clearly violates causality, and of course there is a question of how to restore it. And in the literature, there's a known way to do this, and this known way to do this is to bring this equation to the wave-like form. So in particular, what we see here is a second derivative term that is not compensated in space, that is not compensated by a second derivative in time. And what we can do is we can add a second ordering derivative in time term. And when we add it, what we see here is that we get an equation that now has as its support the diffusion equation. So at very low frequencies, this term is irrelevant, and we end up with a diffusion equation as we wanted. But if we look at very high frequencies, this term is less relevant than that term. And what we have now is a wave equation. And when we have a wave equation, we can make the propagation speed to be smaller than the speed of light by tweaking this parameter over here that customer is called the relaxation time to be sufficiently big. And when we do this, we end up with a causal and stable theory. And this equation that we get in this way is called the telegrapher's equation. It's one of the classic mathematical physics equations, but it's also an equation that you explicitly see when you do Miller-Israel-Stewart or Bayer-Romachka, Stefanov, Serantes, and Son approach to second-order relativistic hydrodynamics. So what I want to signal here is that we went from the equation that violated causality to the equation that in principle is causal. But the price that we paid is that we had to increase the order of the equation by 1. So now when we look at the retarded two-point function of the problem, of this problem, what we're going to get is we're going to get a different structure of singularities than we had here. So here, we're only going to get one singularity, and the singularity is going to be basically omega equals minus I dp squared. Whereas here, when we plug the Fourier decomposition into the description of the system, we're going to get a quadratic equation in omega. So we're going to get two singularities in our retarded two-point function. And now this d in the context of relativistic hydrodynamics is going to be related to the value of the shear viscosity here. So now let's look again at this complex frequency plane. So again, the y-axis is the imaginary part of omega, the real axis is the real part, the x-axis is the real part of omega. And we have this two solutions. So like there are two solutions of this equation for omega. And at very small value of p, what we have is that we have a solution that becomes arbitrarily long-lived. So we have a gapless mode, we have a hydrodynamic excitation, the diffusive excitation. And we have also an excitation that is exponentially damped. And this exponentially damped excitation decays over a time scale of given by the relaxation time. And now what happens is that the momentum is an external parameter in the problem. It's related, say, to what kind of initial conditions we have in our system. And as we vary the momentum, these singularities, these modes, change their position in the complex plane. And in this particular setup, as we increase the momentum from close to 0 to some larger value, these two singularities collide. And this collision occurs here at the real value of momentum. When you look at the exact solutions of these equations, this happens when this branch cut over here vanishes, and the two modes then meet on the imaginary axis, and each is exponentially decaying with the same decay rate. And now, after this mode collision, at larger values of momenta, these modes change their behavior, and for modes that are purely oscillatory, they behave as modes that are, purely decaying. They start behaving as modes that are decaying, albeit at half of the ordinal rate of the transient mode, and also propagating as dictated by the wave-like nature of the modified equation. So what one sees here is that in this causal equation, relativistic hydrodynamics also is not by itself, it comes accompanied by a transient excitation, similarly to what we saw in the case of the Bjorken flow. And it knows about this additional excitation because the two excitations become coincident at some particular value of momentum. And as a result of this coincidence, the hydrodynamic dispersion relation acquires a singularity of a branch type, of a branch cut type. And this branch cut singularity means that actually the frequencies in the problem live on a multi-sheeted, in this case, two-sheeted Riemann surface. And when you go from the sheet on which you view this as a hydrodynamic excitation to the other sheet associated with this branch cut, then it turns out that you recover a transient excitation of your system. So, in other words, and this is what Ben pointed out, also at the level of linear response theory, relativistic hydrodynamics knows about the existence of transient excitations, and it occurs through mode collisions and through branch cut types singularities in dispersion relations. So the general take-home from this is that you can think about the low momentum expansion of hydrodynamic dispersion relation as a linear response theory counterpart of hydrodynamic derivative expansion, with the leading term in this case originating from shear viscosity. And this momentum, this momentum, low momentum expansion has a finite radius of convergence that in this talk I'm going to refer to as capital R. And this radius of convergence is determined by the mode collision closest to the origin. This mode collision does not have to occur at the real value of spatial momentum. In general, it's going to occur at a complex value of momentum. And furthermore, the hydrodynamic excitation and the transient excitations live on different sheets of, in this case, the same multi-sheeted Riemann surface. So these are the general take-homes that I here illustrated using a very, very simple example that originates from MIS BRS3 formulations of second-order relativistic hydrodynamics. So before I pause for questions, let me start with 3 motivating questions for the rest of my talk that can be summarized as getting most of what we just saw as mode collisions. So one thing that we've seen is that the derivative expansion of relativistic hydrodynamics, as witnessed by linear response theory and dispersion relations, have a finite radius of convergence, is a convergent series within some region of a complex momentum plane. Whereas the spatial derivative expansion, which is more relevant for the direct description of dynamics, seems to be asymptotic, and how to reconcile these two facts. Furthermore, what we saw on an example is that in a causal theory that contains relativistic hydrodynamics, and this was this telegrapher's equation, the hydro mode, so the diffusive mode, came together with a mode that was transient, that was exponentially decaying, at least at low value of the momentum. And is it a necessity, or it's something that can be avoided? And the third thing that was not posed on this slide as a question is, can we cleverly use these sort of ideas to start what I want to refer to as bootstrap program for relativistic hydrodynamics. So these are the three things that I want to spend the rest of my talk discussing. Are there any questions?
This is so when we talk about demanding that our theory of hydrodynamics be causal, this is only an issue if we also insist on being able to look at arbitrarily high frequency modes, right? So I think in most non-causal theories of hydrodynamics, if I only looked at low frequency behavior, I don't see that it's not causal. Is that correct?
Well, you'll see that causality is going to have actually a non-trivial effect on what are allowed transport properties in your system. So I would say that this question is subtle, that there are, from the point of view of effective field theory, also in relativistic hydrodynamics, there's going to be UV constraints that come from the fact that your underlying theory is causal. So maybe what I should say is that there are several layers of causality that you can talk about. So, but the underlying notion of causality that I want to always have at the back of my head is that when we talk about relativistic hydrodynamics, the relativistic hydrodynamics does not come out of nowhere. It comes because we have some underlying quantum field theory that is relativistic, and we're looking at it in the regime where relativistic hydrodynamics is the right effective way to describe it. But causality, I want to take it to be always there. And now, of course, you can ask, like, if it matters that relativistic hydrodynamics as a standalone effective field theory is causal or not, but that's sort of like a separate question.
Okay, that's what I wanted to hear. I'm happy. Thanks.
Yeah. Anything else? Okay. So let me continue. So I want to first briefly signal for you like the resolution of a conundrum about convergent momentum versus asymptotic real space gradient series. So the basic idea is the following. We can discuss linearized hydrodynamics easily. I mean, like it's something that's been around for a very long time. So what we do is we look at small perturbations of velocity and say energy density, and we don't really impose any symmetry assumptions on them. We just linearize on top of an equilibrium configuration. And when we look at this problem more closely, it turns out that in linearized hydrodynamics, the hydrodynamic constitutive relations can be written only as only three contributions at each order. So there's going to be three tensorial structures that are going to matter for you. And then on these tensorial structures, there's going to be three differential series that generate for you derivative expansions. And it's not very difficult to understand why it has to be the case. If you think about linearizing equations of motion for relativistic hydrodynamics, what you're going to see is that there's going to be this shear diffusive mode that you've seen. And then there's going to be also relativistic sound wave modes that you also see. So, but the sound waves can move, in two different directions, right? Like they can move to the left or they can move to the right along a particular spatial direction. So actually, there's going to be two frequencies associated with them. So from the point of view of mode counting, there's going to be three modes in your dynamics: one shear diffusive mode and two sound modes whose frequencies are going to be complex conjugates of each other. And by the virtue of the counting of real parameters present in this problem, for the shear mode, there's going to be one real parameter at each order. For sound wave, we have in principle, we're going to have in principle two parameters. In the end, we're going to come up with the idea that there's going to be only three tensorial structures in relativistic hydrodynamics at the linearized level, with 3 derivative terms. And what's important is that these derivative terms appearing here, we take them to be purely spatial. So what we're doing here is we're doing a version of the derivative expansion that is purely spatial. And this is something that we can do because our background on top of which we linearize already breaks Lorentz invariance. So that's perfectly allowed. And now, when we have this kind of constitutive relation, it turns out that using spatial derivative expansion allows us to directly translate the property of these differential operators when acting on a solution of equations of motion on the properties of the dispersion relation and the radius of convergence. So how this works is the following. So we look at this case that boils down to be telegrapher's equation. So in the context of relativistic hydrodynamic description, this is going to be MIS or BRS3. So we have a hydrodynamic excitation that we've already seen, and we have a non-hydrodynamic excitation that we've already seen. And we look at initial conditions for our dynamics, such that, I mean, we look at the dynamics in which, say, there's a motion along one spatial direction that depends also on time, because we're interested in dynamics. And our initial condition is such that I believe energy density, let me see. Yeah, sorry, I forgot like exactly what we took as an energy density, but I believe it might have been non-zero. What's important for me is that the support of the initial conditions is in momentum space is going to be compact, which is that we're going to assume that our initial conditions are only supported in momentum space between vanishing spatial momentum and some finite momentum that I'm going to call Pmax. And what we do is we look at the derivative expansion of associated with the hydrodynamic constitutive relations that we introduced. And this derivative expansion is going to be at a given position is going to be just some number at each order. And what we do is we perform a ratio test of the convergence of the series by taking the ratio simply of the coefficient at n+1 order versus the coefficient at nth order. And we plot it as a function of the order. And now the control parameter in our problem is the support of the initial conditions in momentum. And now, sorry, just to jump in, the energy density decouples from this problem. So like the velocity is the only degree of freedom. That's why I wrote it like this. So like that, this is all there is to solve the initial value problem. Only this function and that function, and this is the telegrapher's equation problem. So like there is no energy density in this channel. So now when you look at this ratio test, you know, if the ratio of the two subsequent terms at large order approaches a constant that whose absolute value is, I mean, the absolute value of this ratio approaches a constant whose value is smaller than 1, then the series turns out to be a convergent series. It's going to have a finite radius of convergence. And it turns out that this is the case when we take the support of the initial conditions to be smaller than the value of momentum associated with the mode collision. Now, when the support of the initial conditions in momentum space extends past the momentum, past the value of momentum when modes collide, the ratio test is the outcome of the ratio test is gonna depend on the support of initial conditions in momentum space, and in particular, the support of initial conditions in momentum space extends past the value of momentum when the two modes collide. So when these branch cuts are when these square root functions are equal to each other. And sorry, they vanish. So like when we just have these terms, so at P equal R, when this support is larger than that, then we see that our series does not converge, but it does not converge in a parallel manner. And now when the support of initial conditions extends all the way to infinity, so basically this theta function here goes away, then the ratio test produces for us the factorial divergence. So this conclusion turns out to be a super general conclusion that we proved in our paper. So the punchline of this study is that this mode collision scale is a natural scale of breakdown of hydrodynamic effective field theory that leaves a clear imprint both in its native momentum space as well as in the real space, as you saw on this plot. Any questions?
Wait, so before you had this picture of the two modes, and you could look at it for P greater than R.
Yes.
But, so what are you saying happens at that point? Is there just some UV description of instead of hydrodynamics, or can you say what you mean by that region again?
Well, I mean, in this talk, I always think about hydrodynamics as embedded in some larger framework, right? So here I was thinking about this telegrapher's equation as my physical microscopic description, so to speak, QCD or n equal to 4 super Mills. And I isolated from it a mode that behaves hydrodynamically at low frequency, at low momentum, right? And I also know that there's a mode that behaves non-hydrodynamically. But then I look at the problem of solving, the equation exactly for this kind of initial conditions, and I interpreted the answer in terms of what happens with the modes. So from the UV point of view, there is, like it's just a feature of the description. But from the point of view of hydrodynamics, right, like there's something interesting happening at this point, as you witness from the point of view of what happens with your derivative expansion. The derivative expansion knows about the fact that there are other excitations in the system to the mode collisions. Okay.
Well,
sorry, please go ahead.
Just because my expansion becomes asymptotic instead of convergent doesn't mean that it's not a good expansion to describe the physics. Right? I mean, we use asymptotic expansions all the time, and we get very accurate answers.
Well, I never subscribe to the point of view that it's not good for physics. I mean, it's just a feature that the expansion behaves this way or the other way. And in particular, the fact that hydrodynamic grain expansion in real space has a vanishing radius of convergence, is an asymptotic expansion, implies that it can work much better. It can extend to regions of much bigger derivatives than you would have expected from a convergent expansion. So, in a sense, it's a good thing.
I guess I'm just trying to, like, typically when we say that our EFT breaks down, we're really saying that it can't describe the physics anymore, right? Not that it's transitioning from a convergent to an asymptotic expansion. Well,
I mean, I would say that like in effective field theory in general, you don't have as much control as one has here in the simple differential equation, right? So I would expect that in the context of EFT, like there's like a lot of lore happening when it comes to what you exactly say, in a sense that like you maybe generate like a few lowest terms in the expansion and then you extrapolate from it, right? So clearly, I mean, what's a fact is that in this setting we have a lot of control over. I mean, we can compute almost anything we want because the setting is so simple. But what we have as well is we have a way of approximating our problem as a derivative expansion, and this derivative expansion is going to give us an answer is going to give us a prediction. This prediction is going to deviate from the exact answer depending on initial conditions. Is going to deviate one way or the other. And then depending if the series is convergent, divergent, or has a vanishing radius of convergence, then there's going to be different properties how well the derivative expansion is going to describe the physics of the problem. But of course, generically, you expect that your initial conditions are going to have support up to arbitrary short scales, even like if the support is very small there. And then, like generically, I expect that this actually is the relevant behavior.
Okay, and I didn't mean to derail you.
Yeah, and like the punchline of this is that these mode collisions, as exotic as they might have sounded initially, they leave a very sort of very they leave an imprint in real space that you can sense by computing sufficiently many terms in derivative expansion. So we have these mode collisions, and of course the question is what we can do with them. And now I come to the papers that appeared in the course of the past several months. So let me discuss now causality and retarded two-point function. And of course, the perspective that I want to advocate is that we are in some microscopic description that is a quantum field theory, say, and that it obeys the laws of causality. So in particular, if we calculate the retarded two-point function, this retarded two-point function of a local operator is going to vanish outside the future light cone. And it turns out that this strongly constrains the position of singularities of retarded correlator in complex omega and momentum, so frequency and momentum plane. So in particular, when you look at the Fourier transform, the singularities in momentum spice cannot lie where the Fourier integral converges, right? Because if the integral converges, then you get just some number, and singularity is not something that is just a number, right? Like it's a blow up of your behavior or something exotic happening, not just a regular number. And now, what you can do is you can look at precisely the loci where the Fourier integral converges for complex omega and complex p. And assuming the retarded two-point function does not explode exponentially in time, we get that this object is going to converge, provided the imaginary part of the frequency plus the absolute value of the imaginary part of the spatial momentum are smaller than 0. So if this object has singularities, these singularities, so in other words, modes, must obey this relation. So their dispersion relation, minus imaginary part of the dispersion relation plus absolute value of the imaginary part of the spatial momentum must be bigger than 0. And this inequality is not new. You can find it in in algebraic quantum field theory books. You can find it in Hack book, for example. But the inequality turns out to be super constraining when it comes to what relativistic hydrodynamics is gonna do for you. And this is the subject of the latest papers that we wrote. And the inequality is also not new, because when discussing this picture that appeared on my 6th transparency, I assumed that the spatial momentum is entirely real. And you see that all the singularities lie on the negative imaginary part of the complex plane. And indeed, like if you take P to be real, then this is 0. And the imaginary part of omega has to be smaller or equal, smaller than 0. And this is precisely what you see here. So this inequality is not new. But what it has are new applications. So of course, like we can think like, where is the key novelty? Like, where is the key thing that allows you to make progress that stems from this inequality? And when you think about it, it is that we allow in this inequality for the momentum to be complex. So typically you don't do this, but the complex momentum means that not only we have one inequality for each absolute value of momentum, but for each absolute value of momentum, we have infinitely many inequalities that are parameterized by this phase angle theta. And when we have an infinite set of inequalities, all these inequalities together can be actually quite constraining when it comes to the functions omega of p. So, yeah.
Hang on, can I ask, is this you're assuming that omega of p is an analytic function in p? Is that what happened?
So here I'm not assuming anything.
Yeah.
The assumption is gonna come here.
Okay.
Yeah.
But I mean, when you say that you have all these extra inequalities, these are inequalities on the behavior of omega of p at complex p.
Exactly.
Right. So you have to assume that the behavior of omega of p at complex p is somehow connected to the behavior of omega of p at real p. Otherwise, these are useless inequalities, right?
That's true, but like this is the case in all the examples that we know.
Okay.
So
sure.
yeah.
Okay.
Yeah.
Thanks.
Yeah. Yes. But I mean, in particular, we know that like in all the examples when you do calculations, omegas appear, in a way that allows you to I mean, in a holomorphic way, like you just have omega appearing, not like absolute value of omega or anything like this, right? So as a result, like this is a natural step to go from real omega to complex omega. And similarly from real p to complex p.
Okay. Thanks.
So we have like this infinite set of inequalities, and let's focus on the series expansions of such omega of p, so the position of the singularity at small p. So this is an assumption that this expansion has to take this form, but this expansion, this assumption occurs is realized in holography. Is realized in all the theories of relativistic hydrodynamics, such as MIS, BRS3, BD, and K. And is also realized in RTA kinetic theory, as we know, because of the work by Paul Ramachka himself. So what we want to do is we want to impose this expansion at small p. And we want to assume that this expansion is valid within some complex disk in complex p plane. And now, when we have such an inequality, what we can do is we can take a linear combination of any number of them in an appropriate way. And in particular, we can multiply them by a non-negative function in such a way that it's going to pick up for us basically a single Fourier component. And when it picks up for us a single Fourier component, it turns out that the single Fourier component is going to be basically an absolute value of the coefficient appearing in this expansion. And the coefficient appearing in this expansion is going to be then directly related to the transport coefficient. So when you run the crank using Fourier orthogonality, we get an inequality for each coefficient in this expansion. And this inequality is valid for any p within the convergence radius. And because of inverse powers of absolute values of p's appearing in this inequality becomes the strongest as p approaches the convergence radius. So in other words, like it's the strongest inequality when we take the absolute value of p to be r, to be the value that we know otherwise would correspond to the mode collision. So so this was quite general. This covered both hydro and non-hydro because we start at p to the 0, so we can have an offset in our frequency that is going to make it not gapless. And now, we have this R that we introduced, but of course you can ask, what would happen if we assume that R is infinity? And of course you can do this. So you can take R to infinity. And when you do this, this inequality forces all ANs apart from A0 and A1 to vanish. So the conclusion is that the only dispersion relation that is consistent with causality and infinite radius of convergence is the trivial one that would correspond, for example, to a sound wave propagation in ideal, so perfect fluid mechanics, or that would correspond to singularities that you encounter in two-dimensional conformal field theory for retarded two-point functions of primary operators. So since such a dispersion relation is trivial, and in dissipative hydro, the dissipative corrections appear at terms of the order p squared and higher, omega of p of dissipative hydro must have a singularity in the complex p plane at some value of p. And when you come back to the original inequality, it turns out that isolated singularities in omega of p, in fact, do violate the master inequality. So they are ruled out. So something like an essential singularity or a single isolated pole singularity that would set the radius of convergence over here is out of question, cannot appear. So as a consequence of this, the only singularities that are allowed in omega of p are either branch point singularities or singularity accumulation points that would set R. And in all the examples that we know of in the literature, these are always branch points. And what we know from branch points is that branch points lead to other modes via other Riemann sheets. So sort of what I'm discussing here is a sort of physics proof with this possible caveat that causality and dissipation in the context of relativistic hydrodynamics implies the existence of other modes in the system that, in fact, is the only way we know of making the equations of motion of relativistic hydrodynamics causal and stable. And this is what we saw here. We had diffusion. So this diffusive behavior violates causality because the dispersion relation is not at most linear in P. It's already quadratic in P. And we knew that we could cure this causality curse by introducing the other mode that's gonna make the system to have now two modes that basically live on the same Riemann sheet, albeit on the same Riemann surface, albeit on two different sheets. And the branch cut nature of singularity in omega of p is precisely what allows us to go from one sheet to the other, is the defining feature.
So can I ask a question on this?
Of course.
So there are these works by Pavel Kovtun and Michal and Noronha where they do first order viscous hydrodynamics. Doesn't that contradict what you just said?
No, there's a caveat there. So this is a nice series of works. However, when you look into detail, what they do is they allow you to, they allow for a different than Landau frame in your constitutive relations. And this allows you to avoid the problems that you have in the Landau frame. So in a sense, this allows you to cure the causality issue of Landau-Lifshitz hydrodynamics truncated at first order. But the price that you pay when you look at the differential equations in more detail is that your PDEs become second order in time. So because you have PDEs that are second order in time, you have not only hydrodynamic dispersion relations, but you also have, you have to solve quadratic equation or maybe cubing equation if you look at this in details. And then you have additional modes that come on top of your hydrodynamic excitations.
So you're saying that first order hydro is really second order?
I guess the first one has to be very careful what one means. So what they mean by first order is truncated at first order in derivatives, right? But when you look at equations of motion, you still have to act with conservation. You have to generate conservation equations, right? And then you act with one more derivative. So as a result, like when you look at the equations that they get as PDEs, these PDEs have they are hyperbolic, but they have one more time derivative with respect to what you would expect in the diffusive problem, say. Yeah.
Thank you.
Yeah. So it's basically semantics. I mean, like what they do is in my view some different version. I mean some hidden version of what Israel and Stewart or Miller, Israel, Stewart did. So they introduce additional degrees of freedom, albeit in physical number in 3+1 dimensions. It's less additional degrees of freedom than you do in MIS. And then perhaps like this is beneficial for some purposes, but the idea overall is the same. Yeah. Okay, so let me move to the last part of the talk and finish. So the mindset in 2000s was like either to compute first and second order transport coefficients for various microscopics, or to talk about the bound on shear viscosity. And like this bound on shear viscosity is a very interesting idea. And in this latest work, we wanted to spiritually continue this idea further. So so what you saw in my previous slides is that the set of inequalities allow you to constrain coefficients and dispersion relations of relativistic hydrodynamics. So now if you focus on relativistic hydrodynamics, this A naught, so the thing that is in general not gapless, like we want to get rid of it, right? So like we kill it. And these are the inequalities that we had in our December paper. And now when you look at it, you gain in detail, you gain a new perspective. So actually, you can think about these ANs as an infinite dimensional space of potential linearized hydrotransport coefficients, right? And I'm not here super precise because A1 would correspond, say, to the speed of sound, right? But it's not really transport coefficient in the exact sense of this word, but it's related to the microscopic properties of the system. Say A3 is going to be related to the sound attenuation rate. In general, is going to have a contribution from both the shear and bulk viscosity, etc., etc. But all these things are related to transport coefficients. And now this inequality here, what it tells you is that anything that lies outside a hypercube, infinite dimensional hypercube of this form, violates causality. So lies in a swampland of microscopic descriptions. It cannot really originate from a microscopic description because it violates causality. And therefore, if you adopt this new perspective, the inequality that we reintroduced, when you impose it, means bootstrapping relativistic hydro, that is excluding potential dispersion relations by the virtue of causality alone, without really looking what kind of microscopic description it comes from, whether it's kinetic theory, holography, or something else. And what should come to your mind is, in particular, this picture that comes from a very beautiful paper that is already 11-year old, in which they use the virtues of conformal symmetry in 2+1 dimensional conformal field theories. And they were looking at what pair of the lowest and second lowest scaling dimensions are allowed by the virtue of conformal symmetry. And what they saw is that there is excluded region in the space of parameters in conformal field theories. They haven't really told you, okay, I'm like, we have to look here or there, but like there's an excluded region. And curiously, the two-dimensional Ising model seems to lie at the corner, like very close to the corner in the allowed region of the parameter space of the conformal field theories. So what we wanted to do is we wanted to do something analogous in the context of relativistic hydrodynamics. And it turns out that one can do this. So the logic that drew us to this hypercube is to pick a single Fourier mode. But it turns out that there are very powerful techniques that have been employed, in particular in the context of S-matrix physics, that allow you to phrase optimal bounds as a semi-positive definiteness of finite matrices that is obtained by calculating a subset of moments of this quantity. So it very quickly gets rather technical and complicated. But all in all, what happens is you take a dispersion relation. In hydrodynamics, you have two kinds of dispersion relations. You have the shear channel, diffusive channel, and you have a sound channel. And now you look at semi-positive definiteness of matrices. And then when you look at inequalities that you get in the space of your parameters, it gives you these kind of shapes. So this is a shape of an infinite dimensional object that we call the hydrohedron that is projected to the lowest three non-trivial transport coefficients. And what we know for sure is that everything that lies outside this region is prohibited by the virtue of microscopic causality. And what we expect is that things that lie inside this region are the things that are allowed by causality.
It's not clear to me from this. What is the definition of the? How do you construct this matrix that you know has to be positive semi-definite?
Well, I mean, it's. I'm not sure I can explain it very quickly. It's basically a mathematical theorem that we used, and I believe it's probably the best to leave it like this. So there's a set of mathematical theorems that tell you like what is the optimal way of extracting bounds on coefficients of such series, and this is what we applied.
All right.
It's kind of strange. In the S-matrix bootstrap, you basically use causality, which tells you something about the analyticity of the functions, and then you use unitarity, which tells you about positivity or positive semi-definiteness. But here you don't use unitarity. You somehow get everything from causality. Can you explain why that is? Or?
Well, and like we use only causality that guarantees for us positive definiteness, right? Like it's this inequality, and the rest is having. So what you have is like you have a infinite set of inequalities that are parameterized by the value of the magnitude of momentum and the phase, right? So in principle, what you can do is you can take some subset of these inequalities, right? And what you can try to do is you can reduce these inequalities and try to see like what are the strongest inequalities that you can get for a truncated subset of the transport coefficients. And we've been playing these games in Mathematica, and it turns out that we're getting these kind of shapes.
Yeah, I mean, I understand how you got it. It's just a little bit strange that you get a problem that looks so similar with what seemed like such different inputs. But I don't know
because in the end, like the math problem is going to be the same. In the end, the math problem is that you have some density, right? And from this density, you want to extract constraints on the function that comes in to build it, right? So I'm not claiming that the reason why this connection was made is because there is the same exact underlying physics reason. What I'm claiming is that there is a mathematical similarity between these two problems. And what we did is to borrow the tools from the S-matrix bootstrap field to calculate constraints on the coefficients in the expansion of dispersion relations. That's it. But in general, it's a different physics problem, and I don't expect that these two problems are mappable to each other. Yeah. And you can keep yeah. So this is the set of constraints that you get. What's important to note is that the set of constraint is simple and universal only if you express everything in terms of this constant R associated with mode collisions. If you express it in terms of, for example, temperature in a given microscopic, in a given theory, in a given state, it's not going to be as universal. It's going to differ from state to state, from theory to theory. But if you use R, then it applies to everything, which has this form of a dispersion relation. And you can repeat the story for the sound channel. In the sound channel, you have the two types of coefficients. Actually, what I'm doing here is I'm missing a factor of an I. Sorry about it. And you get other kind of shape. And in particular, the sound channel is the most general answer that you can get within a class of analytic expansions of omega close to p = 0. Because what you can do is you can take the diffusive behavior, and when you boost your fluid to the other reference frame, the diffusive behavior gets translated into this kind of dispersion relation. So this form of hydrohedron that we have here is the most general that there is, that applies to holography, hydrodynamic theories, and at least RTA kinetic theory, perhaps something more general. Yeah. So let me try to finish and take further questions. So in the past decade, what we saw is that hydrodynamics and transient excitations are interconnected, and we saw it by the divergence of hydrodynamic space-time gradient expansion in hydrodynamics and by mode collisions. Because of the work that we did in 2020, we know how divergent space-time gradient expansion follows from mode collisions and momentum support of initial conditions. So that we know that the mode collision physics and the physics that was uncovered in the Bjorken expansion are not two distinct phenomena, are actually like two sides of the same coin. Due to the work that we did in last December, we know that causality, encapsulated by this powerful inequality, plus dissipation, basically necessitate the existence of non-hydro excitations, because the only dispersion relations that are entire functions of P are super trivial and are given of this form. So in particular, what this means is that the broadly understood MIS trick, which means that on top of hydrodynamic excitations, you add other degrees of freedom, seems to be always needed to render relativistic viscous hydrodynamics PDEs causal. And as Paul asked, this also applies to BD and K formulation of relativistic hydrodynamics. And in the latest paper, what we did is we used S-matrix bootstrap techniques, but not necessarily the underlying physics, to show that causality, so again this inequality, allows to derive non-trivial robust bounds on transport as encapsulated by this interesting shapes in the space of parameter. The new object that we introduced in analogy with the progress in S matrix and conformal bootstrap is what we call the hydrohedron, which is basically the landscape of transport coefficients in linearized hydrodynamics. So when it comes to outlook, This recent progress that I discussed in my papers, as well as papers of many of my colleagues, points towards a unified understanding of relativistic viscous hydrodynamics in a class of systems models that takes causality, the underlying microscopic causality, as a unifying principle. It also naturally leads to a change of perspective, and this change of perspective is that instead of getting exact values of transport, we focus on what are allowed ranges, what are allowed regions, and this we named bootstrapping relativistic hydro. And what I want to finish the talk with is that the three developments that I mostly discuss in my talk call for a lot of further research. Like, one interesting question is, can one see these mode collisions experimentally? Or even a more primitive question, can we see non-hydrodynamic excitations experimentally? And I know Paul has been thinking about it already in 2015. Secondly, when it comes to the hydrohedron, we only look at constraints coming from the values of the spatial momentum that were smaller than the radius of convergence. And in principle, we might expect that if we impose conditions farther away in complex plane, for example, about the permitted structure of singularities, then the hydrohedron is going to shrink, and like that the true hydrohedron is going to be smaller than we uncovered. But we did some preliminary studies, and it seems that the answer is no, that what we got already are optimal bounds. Of course, what I discuss is linearized hydrodynamics mostly, and there's much more to it. Like, there are nonlinear transport coefficients, for example, lambda1 at second order. And the question is, like, can we get similar constraints for nonlinear transport coefficients? And it turns out that there is an analog of the inequality that I discussed that applies for 3-point functions of stress tensor, or like the three-point functions of operators. And of course, one can take it from there. We have not looked into this. In parallel to what I've been discussing, there's been a lot of interest in the notion of hydrodynamic attractors, so causative relations for relativistic hydrodynamics that resum naive truncated expansion at a given order. These ideas were primarily tested in the context of the Bjorken expansion, where the issues of causality do not arise. But of course, one question one may have is if it's possible, or maybe one should not even bother to get causal equations of motion for hydrodynamic attractors because of what I've just discussed. And the last thing that I want to signal is that the dispersion relations that were input for all the works that I discussed had a finite radius of convergence around p equals 0. But what we know is that upon including statistical fluctuations, we generate terms that have fractional powers of p, which formally at least yield the radius of convergence of the series around p equals 0 to 0. And of course, the question is like how the inclusion of these effects alters the emerging picture based on causality. So that's all that I wanted to say. Thank you very much, and sorry for taking longer than usually.
All right. Thank you very much, Michal. And thank you for the lengthy and detailed talk, which I appreciate. We had a few questions during the talk. Are there any others now?
Go ahead.
I have a question.
Yes, please go ahead.
Can you hear me?
Yeah. Yes.
Okay, good. So you said it seems like this Mueller-Israel-Stewart trick is generally required in order to have dissipation and causality.
Yeah.
Do you have to introduce a pure relaxation mode, or?
Yeah, so that I have not really discussed. I mean, like the point that I wanted to make is that when you start with hydrodynamic dispersion relations, like we know that causality requires this dispersion relation to continue indefinitely and have a finite radius of convergence set by the singularity that in all the cases we know is a branch cut. And therefore, that means that when we take other sheet associated with this branch cut, we're going to end up with other mode that is not hydro.
Uh-huh.
So this is what we imply. And we know that this is precisely what happens in Israel-Stewart. We know that this is precisely what happens in BDNK. And we know that this is precisely what happens in ahydro. We know that this is precisely what happens in other models. Like we had a model that couples oscillatory excitations to the system. So, so I would say that it's. I mean, this is the notion that I wanted to put forward. Like how it happens in detail. I believe this is going to be model dependent.
Okay, but it does allow for, say, oscillatory excitations on these other branches.
Oh, certainly.
Oh, okay.
Certainly.
Cool.
So in particular, we had a model in 2014 in which we proposed like a generalization of Israel-Stewart that instead of adding here like one derivative was adding sort of like two derivatives. I mean, it was a bit more complicated than this. But yeah, I mean, like this theory has causal and stable regions.
Okay, cool. Okay, thank you.
Sure.
Paul, did you have a question?
I just had a comment. I think there is experimental evidence that you have these mode collisions and that they sort of turn real. And I was trying to find the reference here on my computer, but I think in water. So if you look at shear waves in water above a certain frequency, there is a experimental sort of evidence that they turn propagating. And the same is true for shear waves in sort of geoscience, like earthquakes or so. They also have what seems to be propagating shear modes there. So if I dig enough, then I'll probably find the reference. But I just want to add that there is some evidence out there.
I mean, like that's very interesting. I'm like that. I mean, like it's beautiful that these transient modes exist. I mean, like the only caveat that of course there is that here everything was discussed on the premise of causality, right? And whereas like the system that you had in mind are non-relativistic systems, right? So like the origin of the caveat might be that the origin of these mode collisions is different. Although like they manifest themselves at the level of dispersion relations in the same manner. But thanks, Paul. Yeah, I mean, like if you could share the reference, that would be fantastic. I mean, I know of your paper with Gasman, of course, but probably you have something else in mind.
Yes, I have something else in mind. Yeah.
Yeah.
Yeah, I was wondering if you like checked any examples of theories and whether they lie inside your closed regions.
Yeah, of course. I'm like, yeah, I mean, it's yeah. So we look at several examples of theory. So we look at some examples for holography, which we worked out, and we look at some examples from, for example, from Miller-Israel-Stewart. And these theories lie just deep inside the regions that we casted as permitted. So there was sort of like no significance to them. Like what I want to signal is that in the context of this work, interesting things happen at the corner, right? Like I don't think it's settled that the Ising model exactly lies at the corner. It's like I don't know about it, but at least like the phonological observation is that it's perplexingly close to the corner. So like part of the philosophy that we had was to look at corners here and try to identify like if something exciting is happening. And it seems that like the only corner where there is something allowed that we know of is actually a very boring one, and it's this corner and that corner over here. So it's a corner at between alpha 1 and beta 2. So alpha 1 corresponds to the speed of sound. So when you approach 1, you approach stiff equation of state, or you talk about conformal field theory perhaps in 1 + 1 dimension. And beta 2 going to 0 corresponds, of course, to lack of dissipation at the leading order. I mean, there should be a factor of I here. And it turns out that, well, I'm like, this is just this at least linear, at most linear dispersion relation that I talked about. So these corners are extremely boring corners, and we have not managed to identify any interesting corner. But there are interesting things happening at perimeters. So, for example, if you look at if you look at these kind of shapes, what you can find out is that at the boundaries of these regions, so like at the boundaries of these regions, like most of the boundaries are excluded. And it turns out that they are excluded for a very peculiar reason, which is that on the boundaries you can find the exact dispersion relations that lie there. Sort of like the lowest coefficients determine all the higher coefficients. And then you can resum them to the closed form expression. And it turns out that this closed form expression is going to have a singularity in P plane that's going to be a single pole. And this you know that is ruled out, because only branch cuts or accumulation of singularities are allowed in general. And indeed, like these dispersion relations lying at the boundary of hydrohedron violate the inequality that we introduced outside the convergence radius when you look at the into details. So yeah, I'm like we played various games with this object, and everything seems consistent to the best of our understanding.